Hello and welcome back. In the previous slice of physics, we covered a lot of concepts around electric potential and potential energy, and in this video, we're going to reinforce those concepts with a numeric example. We will first look at what the electric potential is near a point charge, then we will see what the potential energy of two or more charges is, and finally, we will take a look at the potential and kinetic energy changes that occur as free charges move in an area where the electric potential is changing. And in tackling this example, we'll introduce you to the concept of an electron volt. In the last video, we talked about the fact that you only need one charge to have a potential terrain, and further, we said that a positive charge sits at the top of a potential hill where the electric potential drops as you move farther away from the charge, and also the slope of the change gets steeper as you get closer to the charge. And we also discussed the fact that a negative charge sits at the bottom of a potential valley that also gets steeper as you get closer to the charge. Now we're going to look at the equations that correspond to this. Electric potential of a point charge, that's written as V, is given as K times Q divided by R, which in terms of the permittivity constant we've discussed before can also be written as 1 over 4 pi epsilon naught, which is the same as K times Q divided by R. So this equation shows us that as the charge increases, the potential near it increases, and as the distance from the charge increases, which is R, the potential drops. And the profile of this equation is what is represented by these graphs. Now we also know that we need at least two charges to have electric potential energy, so let's see what that looks like. So if I have another positive charge that I place over here, the combination of these two charges gives rise to an electric potential energy, which we can write as U sub electric. We used U for gravitational potential energy and spring potential energy. Now we're using U for electric potential energy. And that's given as K times Q1 times Q2 divided by R, where Q1 and Q2, for example, would be the two separate charges that are needed to have potential energy. And a comparison of these two equations tells us that the potential energy is simply Q times V, where I've generalized instead of Q1 and Q2, I'm just saying that the potential energy when a charge Q is placed at a point where the electric potential is V would be given by this U electric, which would be the charge times the electric potential. Another thing this equation tells us is that the potential near a positive charge will always be positive. Because Q is positive, R is positive, everything in this constant is positive, so the potential near a positive charge is always going to be positive and drop as you go farther away from the charge. Whereas when you take a negative charge, the potential near it is going to be negative. When you put a negative charge over here, you're going to get a negative potential value, and that negative potential will keep increasing as you go farther away from the charge, so become less and less negative in that sense, and it'll get shallower as you go farther away. Okay, before we move on, it's probably helpful to take a quick look at some analogies to things that you have learned before. So previously we saw that the electric field of a charge was K times the absolute value of the charge divided by R squared, and you only needed one charge to create electric field, and this equation gave you the magnitude of the electric field. And the force between two charges was given, the magnitude of it was given as K times absolute value of Q1 times absolute value of Q2 divided by R squared. And by comparing these two equations, we got another equation that said the force acting on a charge Q when it's placed at a point with an electric field E would be given by this equation, F equals Q times E. It's helpful probably for you to note the similarities over here. So electric field only requires one charge, so does electric potential, and those equations look very similar. Electric force needed at least two charges, and so does electric potential energy, and those two equations look very similar. And the equation that relates electric potential energy to electric potential, which is given by Q times V over here, looks very similar to the force equation between charges as it relates to the charge times the electric field at a point at which the charge is placed. And one last fact I'll mention is, remember that the electric field and electric forces are vectors, and these equations only give you the magnitude, and we had other rules for the directions, whereas electric potential and electric potential energy are scalars. Even though electric potential can be positive or negative, and electric potential energy, as you will see, can also be positive or negative, they are scalars. The negative sign does not imply any sense of direction. Okay, with all that in mind, let's take a look at this problem. It's asking for the electric potential at points A, B, and C, which are at distances of 10 centimeters, 20 centimeters, and 30 centimeters, respectively, from a negative 10 nanocoulomb charge. That's the first part of the problem, so let's start with that. So I've got the negative charge over here of negative 10 nanocoulomb, and I got points A, B, and C, which are at distances of 10, 20, and 30 centimeters. So the distances between each of these points is 10 centimeters in each case. To determine the electric potential at these points, I need to use this equation over here. Electric potential is K times Q divided by R. So let's do that quickly for each of these points. For point A, I've got potential at A equals K times Q, the charge, divided by R, which is the distance from the charge to point A, which in this case would be 9.0 times 10 to the 9 for K. The charge is minus 10 times 10 to the negative 9 to convert it to Coulomb. And the distance, given in centimeters, I'll convert it to meters. So that'll be 0.1 meters. And when we solve for this, we get negative 900 volts. So there's the electric potential at A. For B, it's basically the same process. It's still 9.0 times 10 to the 9 for the constant K. It's still the same charge, so negative 10 times 10 to the negative 9 to convert it to coulombs. And then the distance of point B from the charge is 20 centimeters. So that would be 0.2 meters, and that'll give me minus 450 volts. And finally for C, I will have VC would be the same K value, same charge, but a different distance. The distance of point C from the charge is 30 centimeters, that's 0.3 meters, and that'll give me minus 300 volts. So the first thing we see is that all of these potentials are negative, which makes sense. We said that the potential from a negative charge in the space around it will always be negative. Secondly, we see that as we get farther away, the numbers get smaller, so it becomes a smaller negative number, which means the potential is increasing, which is consistent with our expectation that a negative charge sits at the bottom of a valley. So let me show that over here. So if that same negative charge is over here, the potential profile around it as a graph would look something like this. So it rises as I get farther away from the charge, and then it gets shallower as I get farther away from the charge. And then let me show the points A, B, and C over here. So let's say this is point A, point B is at an equal distance, and point C is at the same distance farther out. So these distances in each case. So here's my 10 centimeters from the charge to point A, 10 more centimeters from point A to point B, and an additional 10 centimeters from point B to point C. Those distances are equal. The potential values were negative 900 volts over here, negative 450 volts over here, and negative 300 volts over here. So the change in potential, if I want to look at that delta V, change in potential between point A and point B, will be given as the potential at point B minus the potential at point A. It's always final minus initial. So that's minus 450 minus 900. And when we solve that, we'll get a value of plus 450 volts. So the potential to go from A to B increases by 450 volts. And you can see that because the slope is getting shallower, the potential change between B and C is not as high. So I go the same distance out from the charge, but only pick up less potential change. So the delta V In this case, would be Vc minus Vb to go from B to C, and that'll be minus 300 minus negative 450, which when we solve for that comes out to be plus 150 volts. So rather than pick up 450 volts to go from A to B, I only pick up 150 volts to go from B to C. Alright, that part is done, and now I'm going to clear up some room to move on to the next step. Okay, now we have this additional question. It asks that if I place a proton at point B and then let it go, will it fly towards A or fly towards C? What change of potential does it go through? And how, when it moves like this, what are its changes in potential and kinetic energies? So once again, keep in mind that there's a big difference between potential and potential energy. So here we're talking about potential energy and kinetic energy. Here we're talking simply about electric potential. And here are the additional equations I have. I have one for electric potential energy, which is given as K times Q1 times Q2 over R, or simply the charge Q times the potential at the point where the charge is placed. So in this case, I've got a proton that's placed at point P. Proton is positively charged. I've got a negative charge over here, so the proton is going to be attracted to it, so we know that it's going to go from B to A when we release it. And that fits our intuition. If this was the Earth and if this was gravitational potential, if we release a ball, it's going to roll down the hill. The proton does pretty much the same thing. So for a proton, we see that it rolls down the potential hill from B to A. The change in potential it goes through, in this case, since it's going from B to A, the change in potential will be the final, which is A, minus the initial, which is B. So that's minus 900 minus negative 450. So that gives me an answer of minus 450 volts. So it goes through a potential drop. When you release a proton, it's going to go from a higher potential to a lower potential. So the change in potential is negative. The corresponding change in potential energy, delta U, I can either use this equation over here, K times Q prime, or Q1 times Q2 over R, and figure out the potential energy at B, potential energy at A, and get their differences. Or I can simply say that delta U is simply Q times delta V. That comes from this second equation. If U equals Q times V, I've got the initial, got U initial would be Q times initial potential. I would have U final would be Q times final potential. And I can subtract these equations to get UF minus UI, which will be Q times VF minus VI, or delta U equals Q times delta V. So I know the charge. It's a proton, and a proton's charge is plus 1.6 times 10 to the negative 19 coulomb. And the potential drop it goes through is a minus 450 volts. So that'll give me negative 2.4 times 10 to the negative 17 joules. Coulomb times volts is simply joules, which makes sense. The unit of energy or change in energy has to be joules in SI units. Now this is a very small number, and we have another unit of energy that we use, and that's called electron volt. So let's define that over here. Electron volt, which is written with a lowercase e and a capital V, is defined as 1.6 times 10 to the negative 19 joules. Essentially, it's the amount of energy that a proton or electron gains or loses when it goes through a potential change of 1 volt. So a couple of things here that you want to pay attention to. Volt is a unit of potential, electric potential. Okay? Joules is the SI Standard International Unit of energy. But electron volt, even though it sounds more like volt than joules, it is a unit of energy. And so if we go back to this and do the conversion, the change in potential energy would simply be minus 450 electron volts. That's why that unit is convenient for us. If we know the change in potential, and if the charge is 1 electron or 1 proton, the number doesn't change, thus the unit changes for the potential energy to electron volts. And as a final step, we may also wonder what happens to the kinetic energy of this proton as it goes from B to A. Well, we know that if we release a charge, a positive charge, it's going to fly towards the negative charge, and as it does that, it's going to gain speed. Just like when a ball is dropped, as it falls towards the ground, it gains speed. So we would expect the kinetic energy to go up, but let's see if it does that. Well, once we release the proton, there is no external work being done. So I'm taking you back to physics 1 for a second. So external work in this case is 0. The system of the two charges is working as an isolated system. So when work is 0, total energy is conserved, or change in energy is 0. In this case, the only two components of energy I need to worry about are kinetic and potential energies. So the conservation of energy statement changes to delta K plus delta U equals 0. The total change in energy is 0. And we know delta U, so I can put that in here. Delta U is minus 450 electron volts. That's 0. And when I solve for delta K, I will get plus 450 electron volts. So we've answered all the different parts of this question. So when I release a proton at point B, it's going to fly towards A. As it does that, it's going to go to a point of lower electric potential. Correspondingly, it's going to go to a point of lower electric potential energy. And as it does that, because total energy is conserved, the kinetic energy will increase by the same amount. So in this video, we looked at an example of electric potential and potential energy using equations and solving for numbers. We saw that a single charge is enough to create an electric potential terrain around it, and we further in this example saw that a negative charge sits at the bottom of a valley, meaning that the potential around it are all negative, and the valley gets steeper as you get closer to the charge. We saw that numerically. And then we saw what happens when we place another charge. In this case, we took a positive charge and placed it in the potential terrain created by the negative charge, and we saw which way it would go and what would happen to its potential energy and kinetic energy. And we verified for a positive charge that when released from rest, it'll move to a lower potential energy, and in doing that, it'll also move to a point of lower electric potential. Now, we didn't see in this example, but negative charges will also, when released from rest, move to a point of lower potential energy, but in order to do that, they have to move to a point of higher electric potential, meaning that negative charges are like helium balloons, which would roll up a hill when released. And in this example, we also introduced the unit of energy called electron volt. Thanks for watching.